Hey, good afternoon. So today we're going to talk about demand paging. Many of the topics that I kind of postponed throughout the past few lectures will be addressed today. So let's get into it. So what we're going to see is what is demand paging, what are the algorithms that are required to efficiently implement it. We'll see particular implementations of those algorithms, and that's going to be it. So what is demand paging? So very high level, demand paging is using the memory as a cache for permanent storage. So previously we talked about using processor caches as a cache for your main memory. Now today we're going to talk about using main memory as a cache for your secondary storage, and that's pretty much the idea behind demand paging. Okay, now you kind of should be familiar with swapping from 252. The idea was that if you don't have enough memory in your physical memory, then you have to choose a process, swap it to your storage to make space for other processes. Now we can downscale that idea to any page in your physical memory. So you could swap a page from your physical memory to your storage to make a space for another page to come in your physical memory. So I want to remind you of three main facts. The first one is that the virtual address space of each process is huge. So if you remember from the previous lecture, in older generations of older versions of kernel, in a 64-bit system, your process would have 128 terabyte of virtual address space. And that's more than like orders of magnitude more than any physical memory that you can find. But then we also talked about the second fact that the processes usually don't use their entire address space. In the entire lifespan of the process, you probably end up using only few megabyte or gigabyte of your virtual address space. Now, if you look at a very short period of time, not just the entire lifespan of your process, like maybe few microsecond or maybe few millisecond, that range is even shorter. So within a window of few millisecond or few seconds, your process is going to probably address some number of megabytes of its virtual address space, not the entire virtual address space. Now, add to all of those facts the fact that the physical memory is limited. And if you remember from one of the slides that I had in the previous lectures, that I took a snapshot of the number of processes in my system, my laptop, there were more than 400 processes. Now, if each one of them requires some number of megabytes and I don't have enough physical memory, then I will have to basically do something about it. So at some point, I will have to make a choice between having a physical page allocated to process 1 or process 2, because I can't have that. I can't have both of them in physical memory. And this is very similar to the idea that we discussed with processes. So the whole idea behind CPU scheduling was that we have limited number of physical CPUs, but then we have a lot of threads to run. So at any given time, one of them has to run. Now the same thing is applied to physical memory. You have limited number of physical pages, so you have to pick and choose which process, which process gets to use a certain physical page. Okay, so now if we're using physical memory as a cache for permanent storage, then we're back to the previous lecture on caching. So we have to go and map everything back to what we saw in caching. In particular, when we were talking about caches, we talked about the unit of cache, which was block. We said the smallest block is 1 byte, but then usually each block has multiple bytes, 32, 64, or 128, or any bigger blocks. So what is an equivalent of blocks here? Now we're talking about pages. So the unit of caching is page. So we're going to have a page in physical memory or evict a page to permanent storage. Now, what is the organization of our cache? What kind of associativity do we want to have? If you remember, we talked about direct map caches, some number of way associativity, or fully associative caches. Now, when you're talking about physical memory as a cache for permanent storage, we're talking about fully associative cache because any virtual page could be mapped to any physical page. So the address that you have, which is your virtual memory, can go anywhere in your physical memory. So you have fully associative cache. The other question that we have to ask is how to find our data in the cache being now physical memory. If you remember, in processor caches, we had the idea of tagging. So we would look at the tag, and then we would tag every data, every block in the cache with its address, and then we'll search all the tags to find if we have the data. Now, in using physical memory as a cache for permanent storage, we don't need to do that because we already have page tables. So page tables are going to be used as that for that purpose. So for every virtual address we get, we go to our page table to see if we have the translation. If we have that virtual page valid in our physical page. So it's in our physical memory. If we can find the virtual page that we're looking for in our physical memory. And you know, if we are using page table, then the TLB, which was the cache of the page table, is also going to be used to find the data that we're looking. What is the page replacement policy? Let's say we don't have enough space and we want to evict a page. Which page do we choose? We're going to talk about this one, right? When I was talking about page table, about caching in processors, we talked about random, we talked about LRU. So in today's lecture, we actually dive deeper and examine at least 3 or 4 different policies for this. What happens if you miss in your cache being a physical memory? So if you cannot find your page in your physical memory, this means that your page has to be fetched from permanent storage. So a page fault is going to happen, and you're going to go and fetch your page from permanent storage and bring it to your physical memory. What happens if you write? So if you remember, we had 2 methods, write back or write through. With write through, every write would write in the cache and the next level storage in using memory as a cache for permanent storage. This would cost a lot because it means that you're going to write in your memory and you are also going to write in your permanent storage, which is very expensive. So we don't want to pay that. Instead, we're going to have a write back method, meaning that writes are going to only be applied to memory. And on eviction, when a page is going to be evicted, we're going to check the dirty bit of the page and see if this page has been updated. If so, then we will go and write it back to permanent storage. If not, we're safe. We can just throw that page away, assuming that we have a copy of it in our physical in our permanent storage. Now, this is kind of one of the areas that I promised we're going to use. So for the purpose of today's lecture, we're going to see how the valid bit, the access bit, and the dirty bit in our page table entry are going to be used for demand paging. Now, in particular, let's focus on the valid bit. Let's assume that this is your physical memory. And let's assume that this is your storage. Let's say that there is a page here in the storage that has been brought here. So these are the same pages. Let's say this is page number 3. Now, in our page table, we have this translation from, for example, virtual page number, let's say 7 to physical page number 3. And the valid bit is set to 1. So this is a valid translation. If our process accesses virtual page number 7, we're going to come to memory and find it in physical page number 3. Now let's assume that for some reason we want to evict this page. So let's assume we evict this page back to the permanent storage and give this physical page number 3 to some other process. Now we don't need to go back to this page table entry and change everything. All we need to do is to change this valid bit to 0, indicating that if you need this virtual page number 7, it's no longer physical page number 3 because I have evicted that and I have given that physical page number 3 to some other process. So this translation is no longer valid. Now let's say later on my process actually accesses this address and figures out that the valid bit is 0. So at that point, a page fault happens. Operating system wakes up. Maybe we have to bring back that page. So we go through our physical memory. This time, maybe we find some other empty page, maybe page, I don't know, 6. And we bring this page back and put it in memory. So once this happens, now I go back to my page table. I update this guy. This virtual page now is mapped to physical page number 6 rather than 3, and I make this again 1. So this translation becomes valid again. So this is basically demand paging in action, using just the valid bit. Okay, so I just explained these. The valid bit is going to be used to indicate if the translation is valid. If you do evict a page, then you set the valid bit to 0, indicating that this translation is no longer valid. Now, if hardware accesses a page table entry that with invalid bit, then it's going to raise a page fault and trap to operating system, and operating system is going to make a decision. Now, not all these page faults result in termination of your process. Some of them might, if your process is accessing something that is not supposed to do. For example, let's say you have allocated a heap memory for your process, and then your process deleted that, so freed that space, so that translation got invalid, and now your process is accessing it again. This should potentially terminate your process. This is a page fault, potentially would lead to a segmentation fault. If not, let's say if it is because of demand paging, then operating system is going to go and grab your page, fetch it from permanent storage, bring it back to physical memory, resolve the fault, and go back to the instruction that caused this fault, and your process will continue. So on a page fault that is of a sort of demand paging and we want to resolve it, what's going to happen is you're going to allocate a new physical page, load your page to that physical page that you just allocated, update the page table entry, and make it valid, and start executing. Now, what happens if you don't have any physical page remaining? So if all the pages are in use, then you have to pick someone and throw them out, evict them. Now, at that point, you're going to look at the dirty bit of your page. This is where the dirty bit is going to come in. So this one was the valid bit. Now this is the dirty bit coming in. So we're going to look at the dirty bit of the victim page that we have chosen to evict. If the dirty bit is set to 1, then we have to write it back to permanent storage. If the dirty bit is 0, then we can just throw it away. We don't need to do anything. Assuming that we already have a backup of this page in permanent storage, then we don't need to do anything. We already have the backup. Then once we evict the page, we have to go to the page table and make it invalid. We also need to, if you remember, we also have to invalidate the TLB entry for this translation. In older computers, that could mean basically flushing the entire TLB. In new generations, you can just go and invalidate a certain translation. So that's that. While you're bringing a page from disk, this is going to take time, right? So you're going to go and read bytes from your disk and bring them in your physical memory, and that could take a lot of time. So while you're doing this, you don't need to really wait. You could start running another process, assuming that your hard disk, your permanent storage, can DMA the information for you. So this is what we saw in the past. So the SSD, for example, start DMAing the page to memory, and while the DMA is happening, the CPU could go and run someone else. Once the DMA is done, the SSD, your hard disk, will raise an exception, and that would cause an exception handler, or sorry, the interrupt handler to run. Interrupt handler will notify the process that was blocked because of this paging and make it ready, and then eventually the scheduler picks the process to run it again. So here is everything that I just talked in a presentation. So on valid page table entries, you just access your memory to read the byte that you need. If you access a page table that is not valid, then a page fault happens. Now your page fault handler will talk to the device driver to transfer the file, the page from disk to memory. Once this is done, an interrupt handler is going to again be invoked. The disk is going to interrupt the processor. At that point, you're going to go and update your page table entry. It means that the page is now ready in memory. So you go and update your page table with the valid address, and then make your process ready for execution. Eventually, the scheduler is going to pick up this process for execution. And at that point, if you remember from precise exception handling, we're going to go back to the exact instruction that caused this exception, and we're going to execute it. This time, now I have a valid translation, and it's going to go and find the page find the exact byte that you wanted to read from physical memory. Okay, now that was very high level. Let's look at one more specific example. So this is an example where you want to actually load your program, your process first time. If you remember, the chain of events was that the programmer writes a program, they compile it, they link it, and they create this executable image. Where is that executable image? That executable image is in your permanent storage. Now, at the time that you want to start executing it, the loader is going to load your executable image into the physical memory. So that's basically what's going to happen. You're going to load your executable image. Now you're also going to allocate some space for the stack of your process. So you set up now everything in your memory. You're ready to start executing it. At this point, you're going to make a copy of every page, every virtual page that your process has loaded in memory. Because if you remember, I said we're going to have a backup of every page in physical in permanent storage in case we want to throw them away and they're not dirty. We have a backup in the disk. So that's going to happen. So we're going to have a backup of every virtual page that we use. Again, the ones that we are using, not all of them, but the ones that we're using. We're going to make a copy of them in the disk. Now, when you set up your page table, you're going to make your page table entries to point to the pages that you have in memory. Those are valid. And the pages that you don't have in your memory, they're going to be in your disk. Now, this particular example is assuming that I'm using this page table data structure to have a pointer for the pages that I don't have in memory. I have the pointer in disk. So this is not necessarily always true. So some operating systems do this, some others don't. Now this might be a little bit confusing, so bear with me. Let me explain. The page table is a data structure that is primarily used by hardware, as we discussed. So different hardware architectures have their different ways of defining page table. So for example, like what is a page table entry? This is how it is in x86. So this is particular about x86 64-bit. Now, x86 32-bit has its own way of defining page table entries. And a page table is just a bunch of these page table entries. So hardware defines this, architectures define this. Now, operating system is in charge of filling and putting data in the page table. But then the primary user of page table is hardware, because hardware is going to do the page walks. Whenever it wants to translate, we're going to rely on hardware to traverse the page tables. Now, remember that there were some bits here that are not used by hardware. So hardware is not going to use, for example, the software bits. Now, operating system could optionally use these bits for its purpose, whatever purpose operating system has. So this is a data structure in physical memory that is already allocated. Now we might as well use it, right? We don't need to use it. We can have our own data structures for the translation. For example, we can have a dictionary of virtual to physical translation internally for the operating system. Because again, don't forget, operating system has the responsibility to fill the page table, and then hardware will read it. Now, how does operating system fill the page table? Well, it's operating system's internal design, how physical pages are allocated, how you search for empty physical pages, and so on and so forth. So operating system has its own data structures for tracking free pages, for tracking translations, for tracking where pages are in physical memory, where pages are in permanent storage. So all of that, we have our own data structures. Now we could potentially use these software bits to save some physical memory. Instead of having our own data structures, we can use these software bits. But again, it's not, it's optional. You could do either way. So going back, so in this slide, I'm assuming that we're potentially using these bits in our page table to have a pointer to the pages that are not in physical memory. But this doesn't mean that the operating system itself doesn't have its own data structure. It definitely can have its own data structure. So that's the first point. And then the second point is talking about using the page table. OK, now another thing that you have to remember is that page table itself resides in physical memory. So page table is not some crazy registers somewhere. This page table is also it resides in physical memory. So user page tables are going to also be in physical memory. So once we set up our process, when we load the process, we're going to also allocate some physical memory to the page tables of this process. Now, depending on how big the page table is, which again depends on how many virtual pages our process uses, we might use different number of pages for a page table. And potentially those pages could also be demand paged. So potentially we could swap this page out of physical memory. Now, what is this page? This page was page table of some process. So we're swapping a page table to disk, and then eventually we might bring it back. So that's also possible because page table is another page in our physical memory. Now, let's assume that there is another process in the system, the same as process 1. Now, let's assume that our process accesses a virtual page with invalid page table entry. Now, at this point, we're going to initiate the process of bringing this page from disk to memory. So we're going to do that. While we're doing it, we're not going to wait. So we're context switching to process 2. We start running process 2. And in the background, this transfer, this DMA, for example, could happen. So we're going to copy the page from disk to memory. Then we set the translation. So once this is done, I set this new translation and I make it valid. And then I make this process ready. I put it into the ready list. Eventually, at some point, the scheduler decides to run my process, and at that point, I context switch to this process, and now I have the translation. I can start running it. Okay, now let's look at the cost of a page fault. We're going to use the old formula we saw with cache. So average access time equals hit time plus miss ratio times miss time. Now here's an example. Let's assume that that hit time is 200 nanosecond. Basically, accessing memory takes 200 nanosecond. Let's assume that if you have a miss and you have to bring your data back from hard disk, it takes 8 milliseconds. So this is average page fault service time. Now let's assume that your miss ratio is P. Now you put everything in your formula. You're going to get 200 nanosecond for hit time. Your probability of miss times your miss time. Your miss time is 8 million nanoseconds. So you already see the difference between these two, right? One is 200. If you hit, if you miss, you're going to pay a cost of 8 million. Now, let's look at different P's and see how this could translate to EAT, average access time. Let's say 1 out of 1,000 accesses would lead to a page fault. So this is 0.1%. And this is mu, actually mu second. So if you set P to be 0.001, so this is P equals this, then you get 8.2 microsecond. Now compare 8.2 microsecond to your hit time, the hit time being 200 nanoseconds. Your average access time is 8.2, and that's 40 times slower. So your average access time is 40 times slower than your best case. So this is a huge slowdown. Now, what if I want to bring down this slowdown to something like, instead of 40 to 1.1? So 1.1 times slower. So this means that 10% slowdown instead of, this one is 4,000%. Sorry, 4,000. 4,000%. What if I want 10%? What should P be? So if you do that, you get a P that is this low. So your P should be less than 2.5 times 10 to minus 6. This basically means you have to have one page fault every 400,000 accesses. And this should tell you that, you know, page faults are very expensive and you want to avoid them as much as possible. So demand paging should happen very rarely. And if you get to a situation where you start having a lot of demand paging, you probably want to swap an entire process out so that the other processes at least get enough space to run without page faults. Okay. Now let's look at situations that could lead to page fault. Basically, how could we miss in memory? The first one is compulsory misses. So these are the misses that you get when you access the page for the first time. As we discussed last time, there is not much you can do. One of the things that you could potentially do is to prefetch. But you have to be careful when you prefetch, because if you prefetch the pages that you won't use, because prefetching is based on a prediction. You're predicting that you're going to use certain pages. Now, if your prediction is correct, then that's a win because you have already brought those pages to memory, so you won't miss in memory. But if your prediction is wrong, then you have brought pages to memory that you didn't want, and that means that for the pages that you want, now you have less memory. So that's the trade-off. Then the second reason to have page faults is capacity miss. Basically, your memory is smaller than the demand that your processes have. Now, how can you solve this? Well, you can have bigger memory. That's one thing. The second thing that could cause these capacity misses is memory allocation. So let's assume that you have 4 GB of physical memory, and let's assume that you have 4 processes. So you might make a decision to give each process 1 GB. Now, if you have one process that needs more than 1 GB and another process that only needs few megabytes, then this allocation is going to lead to capacity misses, because the one that needs 2 GB and is allocated 1 GB is going to do demand paging on its own pages because it's confined into that 1 GB. So once that 1 GB is allocated, it's going to swap, it's going to kick out its own pages to bring new pages, and that slows down this process. Now, the process that is only using 1 MB is basically wasting that space. It's not being used. So one thing you might want to do is to allocate memory as processes need. Now, that could lead to unfairness, because if you have one process that aggressively uses pages, then that process could slow down other processes, get their fair share. So this is where the trade-off between fairness and performance comes in. How do you make sure that everybody gets their fair share? So the trade-off between performance and fairness always existed. The other reason for page fault that we should consider is conflict misses, but fortunately we don't actually have this because we have a fully associative cache. In a fully associative cache, you don't have conflict misses because all your page could be anywhere in memory. So there is no single set that different memory accesses would have competition for, which happens in direct map cache. So all the different addresses are mapped to the single block. So they're going to be competing with that block. But here, every page could go anywhere. So there is no competition. So conflict misses are not something that we need to care about, because we have a fully associative cache. The last one that we have to consider is policy miss. Now, let's say that your memory is full and you want to pick a victim to evict a page. Now, if you, let's say, randomly pick a page and it turns out that the page that you picked is like a page associated to CLib, which is like a library that everybody uses. Now, if you evict that page, then you're going to get a lot of page misses, page faults, because of the bad eviction you did. Because maybe there was another page that nobody uses, and you could have chosen that page and evicted it, but you mistakenly picked a popular page and evicted that one, and that caused a lot of future misses that we call a policy miss, which basically could happen because of your replacement policy. How can you make that better? Well, you have to have a good eviction policy, which we'll talk about. Which we will talk about next. So what are the eviction policies that we can implement? Well, the first one is random. Now, this is simple, but it's really not good, because you might pick a page that is used a lot because everything is random. So you could potentially do that. And it's going to create really bad predictability for your execution, because if you randomly choose a good victim, then your performance is going to be good. But if you randomly pick a bad victim, then your performance is going to be bad. Usually for TLBs, we use random. One of the reasons for this is because if you remember, we want TLB to be as fast as possible, because we're paying the hit time on TLB for every translation. If you remember, for every translation, we have a TLB hit time to pay. Now, if you want to implement a more advanced replacement policy, then that could mean that you need more hardware, and adding more hardware is going to make your TLB complicated, and making your TLB complicated means it's going to get slower. So that would require to increase the heat time of TLB, and that's not good. So maybe a better option is to just have a simple random eviction. Now, the other thing that you have to consider is TLB is really small. TLB, has, I don't know, 500 something entries. So each one of them that you pick is gonna have a cost anyways, right? So it might be a good solution for TLB to just randomly do it so that we don't need to put a lot of hardware for a smart replacements. Now, the other thing that you could do is first come, first serve. You could pick the page that you brought first, and you can kick that one out. This is kind of fair because each page gets to be cached in memory for the same amount of time, right? Because the first one that came in is the first one who is going to be kicked out. So on average, everybody will be in memory for the same amount of time. But it's not obviously optimal, because what if the first one that came in is the most popular one? What if the first one that was cached is basically the clib page that everybody uses? Now, if I kick this one out, this is going to impact everybody's performance. Now, what is the best strategy that you can have? What is the optimal eviction policy you can possibly have? This eviction policy is called min. This is the optimal eviction policy. Now, how is it going to pick a victim? It's going to look into future and find the page that is going to be accessed the furthest in the future. So the page that I'm going to access the furthest in the future is going to be my victim. Now you can prove that this is the best you can do. If you pick anybody else, then your performance is going to be less and worse than picking the one furthest in the future. So I'm not going to talk about the proof of it, but you can definitely prove that this is the best. But obviously this is impractical because nobody has insight into future. We don't know what's the next access in the future. Now, so you might ask, okay, why are we even talking about it? It's very similar to, all the other optimal strategies that we talked about in the past. So these are just there for point of reference. These are just there for comparison. So if somebody comes up with an eviction policy, then we can see how close it is to the best. Now, usually you get a trace of accesses, and then you can see what min would have done, what minimum or mean eviction policy, which victims would have been chosen by min. If I know the trace, then I can run min on it, and then compare that with other policies and see how good they do. Now, the one that usually is used in practice is called least recently used. The idea is that if I don't know the future, I definitely know the past. So I'm going to look at the pages that were accessed in the past, and I'm going to pick the one that I haven't used for a while. So the one that I used the furthest in the past is the one that I haven't used for a while. So then I'm going to just predict that because I haven't been using this page for a while, this means that I'm probably not going to use it in the future. So I'm going to evict this page. So that's the idea. Now, this seems to be a good approximation of min. It's not exactly min, obviously, because min works with future accesses. LRU works with past accesses and makes prediction based on past trends. But it looks like a good idea, right? Obviously, it's not optimal because optimum is min and we don't have it, but it seems to be a good one. The downside of it is that implementing LRU requires a high overhead because it requires the operating system to know about all the accesses to memory, and we know that this is not possible, or if possible, it's going to have a huge overhead because remember that we're kind of like asking hardware to deal with memory accesses without waking us up, right? Hardware is going to traverse the page table. Hardware is going to cache translations in TLB, and we're not going to be waken up on every access to memory, right? If hardware was to wake us up as operating system on every access, then the performance would be really terrible. And with LRU, we kind of want that to happen because we want to track which page was accessed the furthest in the past. So we need to know the access pattern to all pages. But again, we don't have that information because hardware is going to do it and not let us know, right? Because if hardware was to let us know, that would have great performance impact. The downside of this is that if you really want to implement LRU, it's going to be expensive. So we'll talk about a approximation of LRU today in today's lecture. Okay, so let's now look at some examples before we start talking about approximations of LRU. So the first example is FIFO. Let's run FIFO. So let's assume that your memory has only 3 pages. So 3 pages in your memory. And let's assume that I'm going to give you the access pattern. So this is kind of like the trace of memory accesses. So how does FIFO work? Well, FIFO is going to look at, so initially the memory is empty. So we bring A, then B, then C. Now A and B are going to hit because I have them in memory. Now I'm going to access D. I need to kick somebody out. Who am I going to kick out? In FIFO, I'm going to kick out the one that was brought first. Which one was brought first to memory? A was brought first, so I'm going to kick it out and put D there. Unfortunately, the next access is again A, so I have to kick somebody else. My options are D, B, and C. Well, B was accessed. B was brought up to memory first, so I'm going to kick B out. Then I have D, so it's going to hit in memory. Next is B. B has been evicted, so I have to bring it back. Now my options are D, A, and C. C was the one that was accessed to was brought to memory first, so I'm going to kick C out, and this is going to continue. So overall, how many page faults did I have? 3 here, 4, 5, 6, and 7. So this gives me 7 page faults. Now let's look at the same access pattern and run min on it. So let's see what min would have done. For the same access pattern, A, B, and C are going to hit. A, B are going to hit. Sorry, the first A, B, and C are going to miss. So I'm going to bring them to memory. Now D comes. I'm going to run min. So min means that I'm going to look into future and see which one of the candidates being A, B, and C, is going to be accessed the furthest in the future. Now, if I look into future, I will see that I'm going to access A right after this. What about B? I'm going to access B in 2 accesses in future. And C is going to be accessed 3 accesses in the future. So C is the one that I'm going to access the furthest in the future. So I'm going to pick C. So I will put C out and put D there. Now A, D, and B will hit. Obviously, C will come because it was the one that I evicted, but it will come the latest. Now, which one should I pick? We're definitely not going to pick B, but I don't have anything here for DNA. So let's, because I don't have it, so we're going to pick one of them randomly. In this example, I picked A. It doesn't really matter because I don't know what's going to come next, and then I have B. So for this, the same example in the previous one where I had 7 page faults, in this example I have 5. Was it 7? How many was it? Yeah, 7. So with FIFO, we got 7 page faults. With mean, we got 5. And this is the best you can do for this. Now, how about LRU? How would LRU do on this one? Now, actually, let's run LRU on some other example and then see how LRU compares to mean. So here is an example. This example is designed to make LRU make bad decisions. So let's see how it happens. So let's run LRU. A, B, and C. OK, now we're going to evict one page because we don't have a space. So we're going to look at past. So C was accessed 1 access ago. B was accessed 2 accesses ago. And A was accessed 3 accesses ago. So which one is the one to be evicted? We're going to look into the past. So we're going to evict A. So we're going to put D there. Now then A comes again. So we need to remove someone. D was evicted. D was accessed 1 access ago. C was accessed 2 accesses ago. And B was accessed 3 accesses ago. So I'm going to evict B because it's the furthest in the past. So I'm going to put that. Now, again, I'm going to look at A, D, and C. This time C is the one to be evicted. And you can do this again, again and again and again. And as you can see, with LRU, I'm going to get a page fault on every single access. So 12 page faults in this example. So every single access leads to a page fault with LRU. Now you can do mean. Look at mean. I'm not going to run mean, but you can see. Let's actually look at it. It's a good example. So here we want to do D. So we're going to look at A, 1 access, B, 2 accesses, and C, 3 accesses. So C is our pick. So we're going to evict C. Now A and B are going to hit. Now C is going to come. Now we're going to look into future. D is going to be accessed next. Then is A, and then is B. So B is our candidate. We're going to evict B. Now D and A are going to hit until B. Now C is here, D is here, A is going to be somewhere in the future. So A is the candidate to be evicted. So A will be kicked out, and C and D are going to hit. So for the same example, which previously we had 12 page faults, with mean I get 6, so half of that. So 6 compared to 12. So this is with mean. This is with LRU. So LRU obviously did really terrible on this example. Okay, so let's talk about some interesting anomaly before I talk about approximating LRU. So usually this is what you would expect. So in this figure on x-axis, I don't know why I did that. So On x-axis, I have the size of memory, basically the number of pages in memory. And on y-axis, I have the number of page faults. Now, this is what you would expect. The more memory you have, the less page faults you get. So if I increase the size of memory, you would expect to get less page faults because you will have less capacity misses. Obviously, you have more memory, you should have less competition, you should have less page faults. So this is what you would expect to have. Is it so though? Let's do this. This is called Blady's anomaly. So let's look at a memory with 3-page and eviction policy of FIFO. So this is gonna be, so this is my trace. This is my trace. If you run FIFO on this, you get 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults. You can run it and convince yourself that this is what FIFO does. Now, let me increase the size of memory to 4 pages. So now my memory has 4 pages. Previously, it had 3 pages. And run FIFO again. Again, I'm not going to run it, but let's look at the results. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I increased the size of my memory and I got more page faults. It's kind of looking at this graph, size of memory and page faults, number of page faults, and it kind of increased. So this is kind of like something that I didn't expect, and that's why it's it's anomaly. You want to increase your size and get less page faults, but I increased my size and got more page faults. Now this doesn't happen with LRU and mean, so you can prove that with mean and LRU, increasing the size of your memory will decrease the number of page faults. But as you can see in this example, FIFO is a one that doesn't satisfy this this property. Okay, now we're done with that. Let's talk about implementing LRU. In an ideal world where you actually get to know which pages were accessed exactly, then you could have a simple algorithm for LRU. You could potentially have a list of all the pages in your memory. Every time a page is accessed, you bring it to the top, to the head of this list. And every time you want to evict a page, you go and evict a page at the bottom of this list, because that's the page that was accessed the least. So every time you get an access, you bring them to the top. So always the bottom of this list is the page that was accessed the furthest in the past. It's a page that hasn't been used for a while. So this is basically a simple algorithm if you had information about all the accesses. Now, in reality, though, we don't get notifications every time a page is accessed by hardware, because hardware is going to access the page without letting us know, right? Otherwise, if hardware were to let us know, then it would be just as slow. So what do we do? How do we go about implementing LRU? The algorithm that is widely used is called clock algorithm. How does it work? So we're going to put all our pages around a circle. Obviously, we're not going to do that physically, but then just to understand the idea, we're going to have a clock hand pointing to a physical page. Now, this bit that you see in the slides, this 0 or 1, is the access bit of your page table entry. Now, I want to remind everyone of how this bit was set. If you remember, we had the TLB, and then we had the page table. Now, the hardware would first go to TLB. If it doesn't find it here, then it's going to go through page table, do a walk, eventually find the page table entry, and then set the access bit to 1, indicating that I have accessed this page. Then cache this translation, and further accesses are going to just hit in TLB, and we're not going to do anything with this access bit. So there are two scenarios that could happen. So if operating system checks this access bit, and this access bit is set to 1, it could be the case that this page was accessed once, and that's it. It just was accessed once. Or it could be that this page was accessed once and then frequently ever after, right? Both of these two scenarios from the operating system's point of view are the same. Operating system does not know which one is the case. Is it a page that was accessed only once? Or is it a page that is accessed frequently? Because even if it is frequently accessed, we're not going to know, because hardware is going to hit in TLB, get the translation, and be happy about it, not doing anything else. Okay, now knowing all of that, let's talk about clock algorithm. So let's say clock hand is pointing to this physical page number 4. And let's say a page fault happens. When a page fault happens, I'm going to increment or move the clock hand to the next page, and I'm going to check this access bit. If access bit is 1, I'm going to set it to 0 and get rid of the page, get rid of the TLB of this page table entry, and I'm going to move the handle one more time. I'm going to look at the next one. It's again 1. I'm going to change it to 0 and flush the TLB. And I'm going to advance it one more. Again, I get a 1. So I'm going to make it 0, advance it another 1 until I get to a 0. So now I found a physical page that has access bit 0. What does this mean? This means that this physical page, from the last time operating system set this access bit to 0, has not been accessed anymore, right? So when we set this access bit 0 and evict the TLB, we make sure that if, next time the process needs this page, hardware is going to not find the TLB, and it's going to come to page table and set this access bit to 1. But this hasn't happened. This means that this page was not accessed from last time that we set it to 0. This is going to be our victim. So we're going to evict this guy. So again, what happened was the hand was somewhere. A page fault happened. We incremented the hand. We moved the hand 1 page, we checked the access bit. If it was 1, we set it to 0, we get rid of the TLB. If it was 0, then we stop there. We found our victim. Now, this obviously is an approximation of LRU. We're not really implementing LRU exactly, right? It's kind of like we're dividing our pages into 2 groups. One group is a group that has been accessed in the previous window of time that we checked. And the other group is a group that I haven't accessed in a while. Now, which one of these ones I'm going to pick? I'm going to pick the one that the head is pointing to. And that doesn't necessarily need to be the page that was accessed the furthest in the past. I'm going to just pick one of them that I haven't accessed. So this is definitely an approximation of LRU. Now, what happens if all the access bits are 1? So what happens is you're going to go through all of them once and make them all 0, 0, 0, 0, 0, and then come back to one of them and pick the first one. So it kind of becomes like FIFO, right? So all of them are 1, and then you come back to the one that you started with that you have made to 0, and you evict that one. And then let's say next time you come and all of them are again 1, then you're going to make everybody 0 and come back and evict the one that that you started with, and again and again. So you're going to do FIFO. If every time you come back, all of them are accessed, then you're going to do a FIFO. And you can see that this is definitely not least recently used. It's FIFO, right? So this approximation is not exactly LRU, obviously. It's an approximation of LRU. Okay, so now let's look at this clock hand and let's trace how often it advances. Obviously, we advance the clock every time we have a page fault. So if the hand is advancing really slowly, if it's moving really slowly, it means that we're not having many page faults. So that's a good thing. So if I look at the hand and it's not advancing so fast, it means that my system is behaving well because I don't have many page faults. Now, if this hand is going crazy and moving a lot, this means that I have a lot of page faults. So moving quickly, this means that it's not good. I'm getting a lot of page faults. Now, one way of looking at this clock algorithm is, as I said, is as if we're partitioning our pages into 2 groups. Now, you don't necessarily need to stay with 2 groups. You can partition your pages into more than 2 groups. So instead of having a single bit 0 and 1, you could have multiple options. So this is where nth chance algorithm comes in. This is a modified version of the clock algorithm. Instead of having a single bit, a valid invalid, valid invalid, the access not access bit, we could do better. So, for example, we could every time we could use more number of bits. Every time you access your page, you set the number to n. Every time you come to a page that hasn't been accessed, you reduce n to n minus 1. So if your page hasn't been accessed, you reduce its variable. So every time you access a page, you set the variable to the max, whatever that is, whatever your n is. Let's say you want to set n to 4. If you access a page, you set the variable to 4. Now, let's say that the clock hand comes on this page and the access bit is 0. So instead of evicting it, we give it another chance, but we reduce this number to 3. Now, let's say we go and come back to this guy, and again, it's not accessed. So then we go back to 2. And eventually, we get it to 1. And then from 1, we go to 0. This is where we are going to evict this guy. So we gave this page 4 chances to be used. And if it didn't, then it means that it hasn't been used for a while. So we just evict it. Now, if you pick a large number, if you pick n to be a large number, then you're adding more overhead because your clock hand is going to just keep rotating and updating these numbers to find a replacement. So that increases the overhead of finding a replacement. If you pick a smaller ends, then your approximation of LRU is less accurate. So it's an option that you have. What about dirty pages? Now, one of the things that you can do with dirty pages is to give them an extra chance. So let's say you get to 0, but then you see that the dirty bit is set to 1. You could count this as an extra chance. So at that point, you start writing back this page, and you set the dirty bit to 0. So you know, if the victim page is a page that is dirty, you know that evicting it has a cost because you have to write it back, wait for this write back to happen so that then you can bring your page in. So instead, you could set the dirty bit back to 0 and start the write back, but don't evict it. Go and find another victim. But next time you will come back, this is now a clean page. You can evict it without requiring a write back. Okay, so now when do we run a clock algorithm? So sorry, how often do you run this? One is to run it as I described it. Every time a page fault happens, you run the algorithm. Now, this is kind of fine. The downside of this is that you're postponing the process of finding a victim to the last minute when you actually need an eviction. Now, this means that your evictions could take a while until you pick the victim and evict it. An alternative is to run this asynchronously, regardless of page faults. So you could just run it periodically, for example, and every time you run it, if you find a victim by running basically every time you run the clock algorithm, you're going to pick a victim. Now, what do you do with the victim? You don't need to evict it because there's no need because a page fault hasn't happened. So instead, you create this pool of possible victims. So you always maintain this pool so that whenever the page fault happens, you already know the victim, which one to evict, right? So you always maintain this pool of candidates to be evicted. If page fault happens, you have your candidate. You don't need to run the algorithm. Now, if a page that is in your victim list is accessed, then you can just remove it from your pool and put it back in the pool of non-victim pages. Okay, So let me see how much more I have. Okay, so I guess I don't want to start talking about allocations at this point. So maybe we stop here. I only have a few minutes left. If I start this next topic, it's going to take a while. So we're going to end it here. Thank you for those of you who are attending and those of you who are watching it online afterwards. So take care, be safe. We'll talk to you on Thursday. Bye.